Hello everyone, let's continue looking into the functioning of this particular register, which is again a positive edge triggered register, and try to evaluate the setup and the hold time for this one. Okay, so first of all, let us try to look into the functioning first. So I'll have picked up some waveforms over here. So let's look into the initial conditions. So for example, initially your D input was 0, your D input was logic 1, then it goes to logic 0 and then logic 1. So ideally if your clock was equal to 0, okay, when a clock was equal to 0, this particular thing is basically turned on, and this thing works as an inverter. So whatever you see at the D, X is exactly the invert of it. So whatever you see at the D, the output is the inversion of it, of the input. Okay, now again, whenever clock is 0, this particular MOSFET is basically turned off. So this is off, and this is basically logic 1 that you see over here. So this is turned on, but doesn't matter because it is not connected to the ground. So this is basically on, this is off, and your clock is 0. So PMOS turns on, and the node Y is being pre-charged to logic 1. Because this connection is off, this is cut off. So your node Y is pre-charged to logic 1, and we have drawn it over here. I'll show it. Okay, so this is the node 1 which is pre-charged to logic 1, and Q underscore bar. So since your clock is still logic 0, this is cut off, this is being outside, this is out of question. As a result of that, you have your Q bar which is being at a floating state, which is somewhere over here. So this is your Q bar which is somewhere at the floating state. Okay, the state of the Q bar is not known at this point of time. Now when your clock moves from logic 0 to logic 1, so just before clock going to the rising edge, the D input has changed, and as a result of that, the output of the D input, which was initially the output of this particular inverter, which is the X point, the point at the X has already been charged to logic 1. So the setup time over here determines the time at which this particular input is stable. So before the rising edge of the clock, if this particular point is stable or this particular point is stable, that determines your setup time. In this case, your setup time will be an inverter delay, because that is the amount of time needed to stabilize this particular the voltage at this point. Okay, anyways, I'll get back to that in a moment from now. For example, now your clock goes to rising high. Whenever your clock goes to logic 1, this particular thing stops behaving as an inverter. Your X has been hold to logic 1. Okay, your X point, the voltage at the X node stays at logic 1, and there are a couple of more things that happen. So your clock pin, which is this particular clock pin, is at logic 1. So this transistor turns on. This is already turned on because the X input is logic 1, and as a result of that, the value that you see over here gets completely discharged. Okay, now since this particular node is at logic 0, your clock is at logic 1, this particular node from this point to this point is connected, and this thing behaves as a complete inverter, as a variable, as a logical inverter. And as a result of that, if you see the logic Y, the Y which was at logic 0, now Q bar goes to logic 1. So over here, if you see, the Q bar goes to logic 1, and after the Q bar you had an inverter. So after the Q bar you had an inverter, so you at the value of Q you see at logic 0. So if you see, the value of Q is logic 0. So whatever the D input which was present over here and what we were supposed to send, that is from logic 1 to logic 0, same thing gets propagated from this particular point till this particular point faithfully. So if you see, at the rising edge of your flop, you capture the state of the D input successfully. Now there are some setup time and hold time associated with this particular waveform. So the clock edge, the moment you send the rising edge of the clock, you need the waveform to be changed within a certain window of the clock. You don't want the input to be changed within certain window of the clock. Now let's try to look into that particular window. So for example, this is the setup. So this is the interiors of the circuit that we just drawn. It looks complicated, but it's nothing but the same one. It looks complicated because of the substrate connections that we have done. So you have your D input over here, you have your clock input over here, which is going across through this complete transistor, and finally it is hitting. This is the Q bar and this is the Q. So our intention is to finding out the value of the clock, or finding out that particular window around the clock when your D input needs to be stable. So what we'll do is, we'll try to take this particular as a subcircuit and try to build a characterization setup. So this is your TSPC positive edge triggered flip-flop. You have your D input, you have your clock input over here, you have the output capacitor, you have the power ground, necessary power ground connections done, and then we'll try to characterize this particular flop. So for the setup time, let's try to look into first of all the setup time. So if you look into the waveforms over here, if this was your input signal, the one which we saw in some time back from now, this is your clock signal. So your input was logic 1, and just before the rising edge of the clock, your input goes from logic 1 to logic 0, and logic 0 is the one that we want to capture at the output. So when you receive the clock rising edge, you see the output suddenly going to logic 0. So basically we are satisfying the setup time. Next, if you try to, and this is the pulse waveform, you have the input delay for the D input was 200 picosecond, the input delay for the clock is 300 picosecond. So this is the input delay. So your input start changing from this point. So this is the 200 picosecond when your input starts changing, and this is 300 picosecond when your clock starts changing. So when your input is at 200 picosecond, clock is 300 picosecond, there is a variation. The delay difference between the clock and the data is 100 picosecond. The output is being captured faithfully. Let's try to shift the delay even more. When you look into 260 picosecond, your input is being shifted by 260 picosecond. You are still able to capture your output faithfully, which is nothing but the D input, which is nothing but the logic 0. So your flip-flop is able to capture the D input successfully. Finally, when you move your input signal even more, if you push your input signal even more by 10 picosecond more, which is 270 picosecond, and 300 picosecond is again your clock signal, you still get the faithful output. You're still able to capture the faithful output. Only the clock to Q delay increases significantly high, but your output is not violated. It is still able to get the output signal as logic 0, which is expected from the D input. Now you push your input even more. Okay, in this case still you will get the output signal as logic 0 as expected as compared to the input signal, but your clock to Q delay, the clock to Q delay increases significantly over here. Now we will again change the input delay by 1 more picosecond. If you see at 272 picosecond, finally you don't get the required output. Basically before the clock edge signal, if you change your D input signal some 272 picosecond or a 300 picosecond minus 272 picosecond comes to some value. If you change your input signal by that period or within that window of your clock signal, you don't get the required output. So you expected the output to be logic 0 because the D input is logic 0, but you don't get it. So this is your setup violation. So you need to protect your D input in such a fashion that it doesn't violate the window of your setup for the clock signal. So your setup time over here, which is pertaining to the previous clock waveform or previous clock to output waveform, is equal to 29 picosecond, which is nothing but 300 picosecond minus 271 picosecond. So that's your setup time for this particular flop, which is nothing approximately equal to 1 inverter delay. Next, what we are going to look into is the hold time. So what we'll do is we'll stop at this point and we'll try to look into the hold time value and the recovery and the removal violations from the next video. Thank you.